Where will the quiz be? You all check your timetable here. Because from next week, from week 5, week 6, week 7, the lecture for GC will be in the classroom. Check your timetable. It's under the SDL. Okay? Or check the announcement on the Oli. Will be on the Oli, not in your classroom. Okay? But if I remember wrongly, 1 or 2 class will be here in this LT. Okay? If I remember wrongly, I think D3 is in this LT. Okay? Any questions so far? No, so remember, after your next week, we'll check your timetable again, where's the small group teaching is going to be. We have invited all the different lecturers to come and teach you in a small group teaching setting. Okay, so we'll be completing UAVs today, and this will also be covered in your quiz.
Oh my god, this freaking table like this, where the fuck did this go? My pen is so ultra. Sorry, Miza. Your phone didn't drop. My bag is squashed.
Rahina, chill down, chill. You need to come a bit.
It's recording. You should record.
So, the previous lesson of last Tuesday, I covered with you quite a fair bit on the fundamentals of UVs, whereby you put a light in, you split, it gives you a different wavelength, all these things. And visible range is usually from 400 to 700 meters.
Where's my bottle?
Let's go to where we last left. Okay, excitation, fundamentals, video color. Okay, this one. Will it be given or not?
Yes.
Okay, this one we given, but please be familiar with the nanometer, all these things, the wavelength. Okay, this one here. Remember how to see what is being absorbed.
She's going to say like 1 minute.
Which one is the maximum wavelength?
Chaos.
Okay, so this compound here, the color will be either this wavelength or beyond here. Oh, but because it absorbs the light, this is the only region that doesn't absorb any light, so therefore you see this as a blue. Okay, then we move to standard curve, standard emission. A equals to EBC. This one here, important or not? Very important. Here's small deviation fundamental. Where did we stop? We stop here, right? Sample cell I went through a few. Up to here, detector, right? Okay, so in the UAVs, 4 components so far. I went through a few 3. First one was the light, which is the light source that comes from either the tungsten lamp or the deuterium lamp. And then we have the monochromator, which is either the prism or the graphite. You have to split the wavelength. Then you have the entrance stick that helps you choose the different wavelength to study. And sample cell, okay, recall for UV, what sample cell we use? We use quartz. For visible wavelength, we use glass or quartz. Clear? Now, detector. What's the purpose of the detector for? Tells us the amount of photons or amount of light that comes through. What's the intensity intensity of the light. Okay? So what it does is that the detector is actually a signal amplification. The dynamo will amplify the signal that comes in. Okay. So what this dynamo or photomultiplier tubes are is actually a signal amplification. So this is how the detector actually works. The photomultiplier contains a photoemissive cathode. So this is known as your photoemissive cathode and several diodes in a vacuum. This detector must be in a vacuum, and this is where your source of light comes in. So what happens is that this source of light, the photons, will knock onto this cathode. Okay? These cathodes are very sensitive metals because the light is able to knock out the electrons from here. So once the light knocks out the electrons, it causes the number of electrons to multiply. From 1 become 2, 2 become 4, 4 become 8, 8 become detection here. So what it does is the detector allows the amplification of a signal here. So with this signal here, you can get a reading. So what are the surface of this metal here? Made out of sensitive metals like potassium, sodium, calcium, magnesium, such that the light can knock out the electrons and then bounce off here. So light enters here, bounce onto this surface, it collides with the metal, causes the electron to be shooted out from this dynamo here. So it emits up from here, goes to here, boom. Then down here, hit to give you 2, from 2 become 4, 4 become 8, 8 become reading from here. Clear? Okay? So this is how the fundamentals of the dynamo works. Now, very simple. So what the purpose of the dynamo for the detector? Help to amplify your intensity of the light coming in for your reading. Okay? Okay. Then your instrument has 2 types. One is the single beam instrument, while the other one is the double beam. So the single beam one, which is the much more old one, okay, not so good. I'll still go through with you why. The sample and the reference cells are read at a different time. Now for the double beam, okay, the monochromatic beam is split into 2 components, and 1 beam for sample and 1 beam for the blank. So in this verse, what does it actually mean? So this is what it means. Okay? So a single beam. You have the light source going through the monochromator that selects the wavelength. So this is all entrance slit. You measure your sample cell first. Then it tells you your signal. Okay? Then after that you put in your sample cell. This is the reference. So you measure the reference one time, then you move on to measure your sample cell. So this measurement is done separately. Okay? So for single beam instruments, your measurement is done separately. Later I'll go on to explain to you what is the drawback for this single beam and why is the double beam much more better. So the lab instrument that you use, I believe you see there's 2 sample holders, right? Have you all done the experiment already? Who done already? One of your class done already, I remember. So when you use the instrument, I believe it's the double beam. Okay, now single beam very straightforward. What it means is actually that your measurement sample is 1 sample at a time, whether for reference or for sample. Now, for the double beam, you put in your reference and the sample at the same time. Okay? Light source come in, split the beam into 2. 2 of the same light intensity goes through it, and then you compare, you measure the detector, and then it tells you the difference in the signal. So this one is actually better. Why? Remember, one of the thing or the requirement for the light source is that you require it to be stable. Because electricity current is not going to be very stable. So your light source also may flicker. You can't see in your eye, but in terms of the machine sensitivity, they can sense it. So let's say, I give you an example. When this one run for the reference, the light come out 100%. But when you measure for the sample here, some flicker in the light intensity, the measurement is actually 98%. So there's a difference in your light source. The difference in your light source will result in a deviation for your sample reading. What type of error is this called? Systematic or random? Random. You can't control the electrical light source. You can't control when will it flicker. So this one is a random error. So what actually is being eliminated with double beam? You eliminate the random error. You minimize it. Because why? At the point of time when this measure, both of them have the same light source. Whether it's 100%, 100%, or 98, 98, or 50-50, both both of them have the same intensity at the same time. So both of them will have the same error at the same time. So this what we do is minimize the random error. Both of them have the same error together. So you get zeros out. Oh? Clear? So now you understand the difference between single beam and double beam? You need to explain one more time? One more time, huh? Single beam, you have to measure the sample and reference separately. This will have a possibility of the random error, which you can't eliminate. And how was this improved? We improved this with version 2, double beam 2.0. UV also got upgrade one. Your light source here go through a monochromator filter, split these two beams equally. Now both of them will have the same light intensity, and therefore any error or fluctuation light source will be having the random error will be eliminated. This type of random error you see inside single beam, but not in your double beam. Okay, so how it works, huh? So this one is a 2 minutes video, show you how it works for a double beam. So this is the light source. Tungsten lamp, 375 to 800 nanometer. Okay. Usually for our CDO we just put it at 750. So the light source can emit, go through the entrance slit, then you go to your monochromator. Your lens here help you to focus the specific wavelength that you want. Go to here, focusing lens, monochromator, split it into different wavelength. This axis slit will move up and down to the desired wavelength that you want. Okay, this thing a bit slow. So once you go and select the desired wavelength, okay, then you go through your mirror to split it through. Cannot cut here, sorry. So this is double beam. So what happens here is do the stack splitting. You split it through. One is a sample, the other one is a reference. Okay? And then this one will go through the detector to come up with a signal here. Clear? Okay. So that's for this video. Now, the advantages I have really tried to emphasize already. So here, see, the sample and reference can be measured simultaneously. Fluctuation in the wavelength are compensated for. So this is what I was trying to emphasize. Compensating for any random error that might arise due to the fluctuation of the wavelength. So you're eliminating the random error within the sample and the reference. Clear? Okay, this one here, simultaneously, means you can do it faster. In order to do sample, wait, reference, then wait, and zero again, reference, sample again. One shot, do two. Faster. So imagine you've got 50 samples to do. This one is faster. Now, chromophores. Got hear this one before? What is a chromophore? Chromophores, the sentence here is the explanation. Chromophores are light absorbing species. Can absorb the light. So these chromophores, they absorb the light to cause the molecule to be excited. That's why it's called UV absorption. These are light absorbing species. So a molecule's absorption wavelength depends on how tightly the electrons are bonded to it, depending on the molecule structure. Okay? And shared electrons in the single bond or organic compounds are very firmly held. So usually their light absorption is in the UV range. But this is not the case for double bond. So electrons in the double and triple bond are not so strong, and they are very useful for this study of chromophore. So for chromophore compound in generally, what it actually means is that in order to be suitable for UVBs. So in order to work for UVBs, your compound must absorb the light range between the UV range and the visible light range. So absorbing groups are usually known as your double bond, triple bond, or your aromatic rings. All these molecules are known as your chromophores. Clear? So what's chromophores again? Light absorbing species. What are the molecules that have light absorbing species? Are usually compounds that have double bond or triple bonds. Single bonds, later you will see some single bonds that are possible to absorb UVBs, like OH bond, NH bond, all these things. Okay? Clear? Okay? So in generally, in order to measure, to apply for UVBs, you realize that this instrument actually quite troublesome. You need to have chromophore, you cannot have high concentration. What else? What other problem? You must use the selected sample cell. Oh? So if I want to measure hexane, can I use this one or not? Hexane. You all can still recall POC or not? Can, hexane, 6 carbon, all single bond. Can I use or not? Cannot. Oh, not applicable. So this is one of the limitation. Only must be suitable for chromophores. Alright, so remember, UVBs, compound must absorb light and is only suitable for chromophores. So, molecule containing a chromophore is known as a chromogen. Now let's look at some example. Here, this one here, can you still remember the name or not? What's the name of this compound? Toluene. This is the aromatic ring. This is the benzene ring. Okay, this one here, what's this compound? What's this compound? Oh no, send all of you back to POC here. This propanone, ketone, 3 carbon. Oh, you are so sad. This is sad for the POC lecturer. This one, how many carbon? 6 carbon, which is the hexane. Okay, so now let's look at this one here. This one all single bond, right or not? No double bond. I think I don't need to issue POC again. Carbon only 4 bonds. Okay. Okay, all single bonds, so therefore this one got no double bond or triple bond. Remember, we say chromophores are usually compounds that have double bond or triple bond. Then you can be UVBs active. So this guy here, UVB is active. Why? Because of the aromatic ring. How many double bond I have? 3. This guy here, C double bond O. Alright? So therefore, only these 2 compounds can absorb UVBs. And they are suitable for UVBs analysis. Okay? Hexane cannot. Hexane will look at other instruments to see. So toluene can absorb UVBs radiation as it contains the benzene. Acetone with the double bonds, oxygen can absorb the UVBs. And hexane cannot. This is inside your notes, right? No. Okay, sorry. Okay, copy this one down. Who here go clubbing already? No money, no bluff lah. You also rich one. Okay, you all go clubbing right, then they put the stamp on you right? Correct or not? Then you go inside there, then they shine the UV light, then you can see some image, some of them draw what bird, what cow or so, all this thing you can see right? So all those are examples of chromophore. Chromophore stamps that you can only use under UV light.
Cool.
But you all always shine under the UV, I sure get skin cancer one. I'm not cursing you all. I just teach you all already what. E equals to what? Energy equals to what? What MC square? That one is another subject. My one is E equals to HC over lambda. Lambda is what? Wavelength. What's the wavelength for UV?
7.
Very small, right? Below 400, right? So the smaller wavelength, higher energy, right? No? So the UV light got a lot of energy, correct? No? So it causes all your molecules on your skin to get excited, right? So because your skin now becomes too excited, it causes you like skin cancer lah. This one not I bluff you. This one is really under UVBs. Okay, so those of you go clubbing, always stand, then go shine the UV light. Oh, good luck. Okay? But you all are still young lah, so won't so fast one. You all still young, so your body can repair one very fast. I old man cannot go with it. Okay. Coffee finish already? Okay, those of you have finished, hurry up. Otherwise I shine UV light at you. That one not my problem now, you don't tell me. Hey, toluene can absorb UVBs, isotone also can, because of the C is double bond O. And hexane cannot. Now let's move on. Now move on. Now there's two approaches to the spectroscopic analysis. Two methods. Okay. So I'm going to show you and explain to you. So most of the time we rely on compound that are UVBs active. So that it means that the compound itself is a chromophore. So to measure the light energy absorbed by the ion or molecule itself, most organic compounds they are able to absorb the UVBs because of the C double bond. But does it mean that we only can use this for organic compound? No. I think this week we will go through the tutorial. So what we mean by complex formation is whereby we use a suitable chemical known as a chelating reagent. What is a chelating reagent? Chelating reagent is a compound that can bind onto the metal. That's a chelating agent. So these chelating agents, we do a special modification. The chelating agent, besides binding onto the metal, the chelating agent also have a chromophore. So when this chelating agent binds onto the metal, because the metal itself are not going to be UVBs and visible light range, right? We put these chelating agents to react with the metal to form you this complex. Okay? Once this complex is being formed already, now you have a new species that can absorb the light. Clear? Understand or not? Don't understand? Okay, wait, I draw some diagram.
Nanti like jumble unless like I print from a different style on sorry Liza, I never noticed. I say it's not my fault by the way the table so we just use green lampu. So how do you just pop out gitu kat sini you see tadi dia tengah doa muka
Y'all can see it, right? Okay, so I draw is example magnesium. Magnesium compound itself will not be UVBs or visible active. Okay, then I have this compound here, a 1,2-diamino benzene. Okay, this here, okay, this compound itself is UVBs because it has a double bond. Okay, this one here will be my chelating agent. I believe you all remember this in PIA Topic. Chelating agent. We can form the additive bond onto the metal. What happens is that when you form a additive bond, okay, form the additive bond. Okay, it results in the formation of a complex. So this chelating agent and the magnesium bind together to form you the complex formation. Now magnesium previously was not UV active, right? React with the chromophore, give you a new complex. This is your complex formation. So now this center here will be UVBs active. So this is your complex formation. Clear? Clear or not in this expression now? So this is what we mean by this one here. This one I mean by this one. The lecture notes. Today the projector are not working with me. So this is what we mean by the complex formation. Alright? Clear? So do I need to show you back the visualizer again? You need the visualizer? Only, huh? Okay. So this is what we mean by the complex formation. So this UVB is very suitable for quantitative analysis, not suitable for qualitative. Alright? But then we come and tell you, we can use this for qualitative analysis as well. The application of UV spectroscopy in the qualitative analysis is very limited. Still can, but it's very limited. Broad absorption bands that lack the details of characteristic profile, other absorbing compounds may also absorb over the wavelength. So what this means? What this point tells you that in terms of the application for absorbance, in this application for qualitative analysis, it is kind of weak. Because why? A lot of other functional groups also can have the same absorbance. As long as you have aromatic ring, all your absorbance wavelength will all be around the same in that region, like 400 to 500, mostly the same. So therefore, due to this continuous overlapping effect, like for example, you want to separate a phenol from an aniline, a bit difficult. Because both of them have the similar absorbance, max wavelength. So therefore, it's very difficult for you to identify or differentiate the compound. But it's much more useful for identifying the concentration. So qualitative, very big, but quantitative can apply. Okay? So in terms of quantitative analysis, this one is what type of graph is this? Standard curve. How I know? Straight line cuts through the zero. Okay? So what this plot is, to give you a plot of your standard curve, all the different concentration standards. Then you measure your signal from your sample. From there, you calculate your concentration of your unknown sample. Standard addition. Okay, now we go on to this interference, and why we going to use standard addition. Matrix interference refers to the combination of all other compounds present in the sample. So that's what we mean by matrix in your sample. So for example, in Coca-Cola, I want to measure the caffeine. The rest of other things like the phosphate ions, the carbonate, what else is like that? The coloring, all these are your matrix interference inside Coca-Cola. Okay, so matrix interference occurs when a compound or any other besides the analyte can also absorb the same UVBs. Or then this could be a problem. Alright? So for example, I want to analyze the caffeine spectrum. But then inside there also got another compound, let's say maybe nicotine. Caffeine and nicotine, structure very similar. Absorbance also roughly the same. How? If there is a problem, maybe this UVB's analysis is not suitable. You have to use something else. Okay? So these are some of the limitations. So some of the limitation is whereby when your analyte and your matrix have the same UVB's absorbance, will it be suitable to use this one again? No, because it will give you a false positive. So that's what I'm trying to tell you. So matrix interference occurs when a chemical compound other than your analyte also absorb the same wavelength as your analyte. Now, testing of phosphate content in Coca-Cola. PO3 4 minus itself is not going to be very suitable, so therefore you add a reagent to make the complex formation. And this absorbs in the middle region. On its own, the dark colored Coca-Cola will absorb all the light across the visible spectrum. Okay, so when you see very white color, and a very white color, what is the light that you see in your eyes? The light shine on me, reflect go into your eyes. You're actually seeing the full spectrum of the visible light. Then next lesson, I wear black color shirt. The light shine on me, reflect to your eyes. What light is being reflected from me? Black color shirt. No light. If I wear black color, you wear black color, okay? All the light has been absorbed. That's why you see it as black. You understand? Clear? If you see white color means all the light is being reflected into you. So that's what I mean, on its own. So the dark color Coca-Cola absorbs all the light across the visible spectrum. That's why Coca-Cola is very dark. It absorbs all the light. And therefore this results in your matrix interference. For this example, your blank is Coca-Cola and you have Coca-Cola plus PO4 2 minus here. Okay? So this is actually doing a standard addition. The concentration of PO4 2 minus can be calculated when the measurements of the blank and samples are made. Okay, so blank is purely the adsorbance of your Coca-Cola. Then my sample with this amount of Coca-Cola added in, alright, give you an adsorbance of 0.38. So this difference here is actually the blank corrected, 0.13. Oh? Now the challenges on this blanks collection, okay, is trying to overcome this matrix interference here. So the challenge of this blank collection is trying to obtain the representative of the blank here, make it identical to the Coca-Cola sample without the presence of PO4 2 minus. And this might be very difficult. Okay? So how do you overcome this? You overcome this by having this standard addition method. See, the Coca-Cola sample, but with this PO4 2 minus at different concentration here. So with this different concentration here, alright, your sample with PO4 2 minus, sample here with PO4 minus at different concentration. This will result you to have a plot of this. Okay? So what now we have is the standard addition. Sample plus 1 ppm plus 2 ppm plus 3 ppm plus 4 ppm. So what this is what we're trying to do, to apply the standard addition here. Am I too fast? Okay, repeat again. Sorry to lose you all. Okay, listen. Now, what are we trying to do? Why we need to overcome this matrix interference? It's because this Coca-Cola here, problem here, on its own, dark colored cola absorbs the light across the visible spectrum. A lot of matrix interference. You might get positive, negative deviation. Also do not know why. Put in one moment 0.38, next moment 0.2, next moment 0.5. You don't know why. Don't know whether it's your friend who drink Coca-Cola become like that. Okay, so on its own, the dark colour Coca-Cola absorbs the light across the visible spectrum. Now, see here. So now your sample is actually known as your blank. Okay? Initially, the sample they want to analyze is actually the Coke. Then inside this Coke here, you add a bit more, PO4 2 minus here. And you can see how to correct the difference in it. So this difference here, okay, will be the concentration of PO4 2 minus that you add in. Right? So this is what we mean by blank elimination. Coke without any sample, so this one is not matrix interference. So now you put this one as your reference. This guy here become your sample. You understand? And that's how we're going to derive to here, this one here. So the challenge of the blank correction is to obtain a representative blank to let the system, the UVs know that, okay, I measure this Coke, even though the calculation, the concentration inside the Coke is what you want. But we put your Coke as your blank. Now with this one as your blank, you start to add in all the different standards. This will give you all your standard reference. Blank with PO4 2 minus at different concentration. 1 ppm, 2 ppm, 3 ppm, and 4 ppm. This here will give you this sample preparation, and your graph will be like this. Get it? Okay, so where is your blank? Your blank is actually the one that you want to find here. That's why you will not cut 0. Because that is your Coca-Cola. So in this standard addition, okay, you make your sample become the blank. And then all the other reference standard value increase along with it. So it's sample here. Your sample here, then plus this 1 ppm, plus this 2 ppm, sample plus 3 ppm. Sample here, so this line here is actually all the sample reading here. And all this elevated line difference here is your concentration. S plus 1, S plus 2, S plus 3, and S plus 4. Now how we find the concentration of S? Apply this equation here. When y equals to 0, the y graph is your signal, right? When y equals to 0, it tells you the concentration of the x. But is your concentration supposed to be negative? No, you calculate it will be negative, but your concentration is not negative. Okay? You need to absolute it. Clear? So that will tell you your concentration of your sample. Okay. Now I'm going to introduce to you this linear dynamic range, the linear range, the linearity of your calibration curve. Because remember Beer's law, there is positive and negative deviation. But for your calibration curve, you must make sure that the curve is a linear range. So how do you find out, or how do you ensure that your linear range of or your standard curve is correct and suitable and applicable? How do you determine it? Using what value? Using the R value, okay? Okay, so for example, this is my standard curve range. If my sample is, let's say, so my standard curve range, I started to have plot from 0 to 50 milligram per liter. Then I got this very fantastic boss. He come and tell me, come analyze this sample. Then I ask him, hey, this sample, what's the content inside? He tell me, oh, this one 100 mg per liter. Can I use this calibration curve or not? Can I use or not? Cannot. Why? Concentration of the unknown analyte must be within your linear dynamic range. So if you give me the 100 mg sample, I must say, wow, I must do again. Do a recalibration again. If not, the analyte must be concentrated or diluted, and a new series law standard must be prepared. Okay. So when my boss give me a sample of 100 mg, what are the two things I can do? 50 mg is very borderline. Cannot. Because you see, my calibration curve is under 50. Must be within. So if I want to eat snake, the 100 mg, I must dilute it by maybe up to 25 mg. Then I can do the concentration to measure. Or if I want to add hard working, I re-prepare the whole standard solution again. From 0 to 100, can or not? Cannot. Must be from 0 to at least 110. Must be more. Okay? You try to make sure that your sample is within the calibration linear dynamic range. Alright? So that's the idea about it. Okay, so there's two ways to do about it. If your concentration of the sample is beyond the calibration curve, dilute it. Make it inside there. Or prepare a new series of standards again. And clear? So this one I want to tell you about things about concentration. So be very careful, because sometimes you'll set much more application question. We give you the range, you design a standard curve. Okay? Okay, so now what are the applications for UVVs? Very simple. It has a lot of application. Organic chemistry, oligochemistry, nucleotides. Usually in the biotech, biotech use this a lot. Environmental application, all this food and nutraceutical and pharmaceutical industry. This one will be tested or not? I don't know. I say I don't know. Application. But what I know is the fundamental and theories of it. So that's all for UVVs. Any question? Want me to do a recap? Yes, no, yes. Okay, I'll do a quick one, 5 minutes. Just talk to you, relax. Okay. So, UVVs the range usually from visible light is from 400 to 700. Then, where is the UV? Below 400, very good. Okay. This one here, E equals to HCO lambda. I want to always say this one here, important for you to know. Because this allows you to calculate the amount of energy in the wavelength. Alright? Allows you to calculate the amount of energy per wavelength during etc. This H constant is the Planck constant. This C is the speed of light. I don't know. 6.63 times 10 to the power minus 34. I also cannot remember. But I hope it's given. I hope it's given. Okay? Okay. So in UVVs, is it emission or absorption? Emission or absorption? Admission or absorption? Absorption, okay, if those who tell me admission, I think I have failed you crazy. Okay? So, how many components are there inside the UV list? 4 components. What are they? The light source, monochromator, sample cell, and your detector. Now, what about this Beer's law? Can you recall from Beer's law? A equals to EVC. Okay, whereby E represents the molar absorptivity. D is what?
The distance.
The sample cell path length. How wide it is. What's the distance between the light going through the sample cell? And C represents the concentration. Okay? So what this Beer's law tells you? There's a problem, right? There's a deviation which is not suitable for high concentration. Not suitable for high concentration. Remember that? Okay? This one here, this one we talk about the negative deviation. Okay, so the non-linear curve may be because of the fundamental limitation of Beer's law. Not suitable for high concentration. And it is the 4 different components inside UVs. The light source. Okay, light source, these are the 3 criteria. We want it to be stable, provide a wide spectral range, and sufficient intensity to be detected by your detector. Okay? Now, for the light source, what are the 2 light sources? Deuterium and tungsten. Alright? Deuterium used for UV. Then visible is for tungsten. Okay. Monochromator. Purpose is to split the light into all the different wavelengths. You can use your entrance stick or exit stick to select the wavelength. Okay? This is how it works. And detector. Where's my detector here? There, here. Oh, sample cell. Okay. Sample cell. Remember, UV must use what? Cell. Must use quartz. And for visible, you can use quartz or glass. Now, detector here, we just went through. Detector is usually made out of dino. Dino inside there is a cathode, photoemissive cathode tube that is inside a vacuum. And what it does is that the signal will cause the metal surface to multiply. And this can be detected by your detector here. You do the reading here. Then the difference between single beam and double beam, what's so special about the double beam? Measurable at the same time using the same light source at the same time. Okay, and it helps to remove any random error. Okay, so chromophore, this is what we introduced to you. Chromophore are compounds that has a double bond and are UV visible active. Okay, and then I believe you already understand what is the linear curve or standard curve and the standard addition. And we just introduced to you this criteria. Linearity, linearity, here. Here, linearity of the calibration curve. Okay, always remember that your sample has to be within the calibration curve range. Okay, otherwise, apply these 2 methods. Either you dilute it or you prepare a new calibration curve range. Clear? Okay, that's all I have for you. Good luck for your quiz. I'll see you